there. Riemann sum gives us an approximation arbitrarily close to the actual integral. Self-explanatory and didn't teach as much. I like this one because it gives me a visual idea of how the subdivisions change over the domain of the function. Nicely done. And 4. Well, there's a star over here. I'm not sure if that's
That counts.
That counts? Okay, so that's 4. 4 people like that one the best. And this one had 4 as well. 5? It can't be 5 because that adds up to 11, and I think we're only 10 people in here. Actually, I think we're only 9. No, we're 10. 3, 6, 9, 10. Yeah, 10. All right, the area function. I like this one most because when you moved the points on the left applet, the area was shown on the right applet, very visual. Showed the area had exponential growth. Interesting, we're gonna take a look at that. Showed how the points A and X directly related to the area function. This one got me thinking the most because it showed the relationship of how one graph reacts to the other. Good, nice job. So, believe it or not, you got some stuff out of this. The first time we did applets, I don't know if you remember, I remember it pretty distinctly. You guys came in and you said, I didn't get it. I couldn't do it, I didn't get it. And so this is sort of proof positive that you're making some really good progress in that area. So kudos to you, way to go. Oh, we're snapping? Both. So there's 3 applets, and there's really 3 things that I want to get out of today. One key thing from each applet, and this is the first one. So this is based on this one over here, and I would agree with whoever said I really liked the fact that there were lots of directions. However, it's also a little frustrating because you have to scroll down and then scroll back up and do it. Scroll down and scroll back up, you know what I mean? So that got a little bit old. So then I actually printed these so I could have them next to me and follow the directions, didn't have to keep scrolling up and scrolling down. So this one was pretty cool. You just basically move this over and you could see the integral was changing right down in here. And let's just get another name. What's another name for integral? How could we talk about that in a different word?
Distance.
Distance, not distance.
The area.
The area, right. So this number is really adding up all that shaded area, right, for you. You didn't have to do it, which is great. So you're just scrolling it back and forth. And then something funky happened, right, when we put these right on top of each other, right, and somebody mentioned this, when point A and point B were right on top of each other, the area was 0. And this A and B, remember, I'm going to write on here, represents this number and this number. If you remember when we started talking about definite integrals. And then something else funky happened when I then moved A over here. Whoops, that's B, sorry. When I moved A to the right of B. What happened?
Negative.
The area became negative. That's kind of weird, right? So when I went from A to B, and we talked about this, somebody was doing this probably the other day, when it was 1 to 2, and then we changed it and we went from 2 to 1, things changed a little bit. And that got a little confusing, and this was, I think, hopefully a little bit visual to help you. So why is that happening? Anybody have any ideas?
Is there some formula for it, and that's why?
Yes. You're going to take a look at that in a little bit in tonight's video lesson. Yep. Why do you think that might be? So it's a little unsettling. It's kind of cool to see. Were there any questions down here that led you to maybe think it started getting into, where is it?
1, 6, it has you switch the order.
6 has you switch the order. And that's where you figured it out? That it became negative? Okay. Let's keep going here for a minute and put B. What happens then when B is right here, right? And then what happens as B keeps moving to the right? What's gonna happen?
Maybe more negative area.
Okay, we're gonna start getting negative area, and this is gonna go, it's gonna start going down. Good, okay. What do you think will happen if I put A over here and B over here? What do you think will happen? This will then become positive, okay. What's that?
Weird.
Weird, totally weird. A little unsettling, not so much. One thing, I'm gonna rip this off, actually. So I can write on here. One thing, before we get into the sort of why that all works, I wanna just mention that if we're talking about this derivative, excuse me, this integral, how do you think I would write it if I switched the A and B? How do you think that would look in terms of notation?
dx of fx, fx.
No, good guess. This, remember, represents the function. And what does this part represent?
Oh, the area.
Close. Remember, area is length times width.
That's the
Whoops.
height.
Oh, it's the number
And
of
this
widths.
is essentially the length or the width. This is the width. This is the length of the rectangle. This is the width of the rectangle. Okay, so that's not really going to change anything.
Like a -1.
Yeah, it's essentially a negative times that integral.
You do that one out. Can you just look at how large A and B are and determine whether it's going to be, so if A is larger, it's going to be positive.
A is
Yeah.
not necessarily, because it depends on the function, right?
Yeah.
If much of the function is under the curve, and this is A, and this is B, then that's still all negative. But if I switched it around and put B here and put A here, then it becomes positive. So this doesn't necessarily mean negative, it means opposite. Good, it means opposite. So if it's negative, it becomes positive, positive, no, it becomes negative. Okay. So these two things, we're gonna start noticing in the next couple of days, that if we switch A and B, we're just taking the opposite of the integral. Now, let's throw in another word for integral. What is integral again? You told me a minute ago?
Area between the x-axis.
Area to the x-axis, good. What is derivative?
That is the slope.
The slope. The slope. We're gonna start connecting those two words today. And that's really what's gonna be tonight's assignment, is connecting those two words. Let's hold off on that unsettling thought for a little bit longer and move into the Riemann sum one. And I think Orion mentioned this in his write-up. He said much of this was really review, and that's actually a good thing. That means that you've been doing it so well all along that you didn't have to learn anything new from this, which was cool. So this right here, remember, is telling us that we're doing right endpoints, midpoints, or left endpoints. This is when you're doing your calculator program, right? Left, right, or midpoints, whichever one you're there. There we go. And this is telling you how many you want to do, right? How many of these subdivisions you want. So in this case, we have 10. And I think one of the really cool things, really visual things, was that as soon as I start moving this number bigger and bigger and bigger and bigger, what's happening? The more narrow the rectangles get, and the more accurate my estimate becomes, right? I don't have much over, and I don't have much under compared to when it was like this. Whoa, that's a really bad one, right? That's a A really bad estimate, there we go. Right, there's a lot under here, right? A lot under, a lot under, a lot under. Okay. Did you mess around with this? The upper sum and lower sum? And right now, what kind of sum do I have, do you think?
Underestimate.
Yeah, that is.
It's,
Most of it's on the.
Yeah, most of it's on.
most of it's under, some of it's over. Where does it go from being an underestimate to an overestimate?
When the slope is, no,
The slope is
when the
negative.
slope is getting away from the, like going away from the x-axis.
Okay, so Aiden said when the slope is negative, it's an underestimate. When it switches and becomes positive, it becomes an overestimate. When it switches and becomes a negative, it's an underestimate.
Oh, unless
Well,
it's
it's
under
an
the
over-
x-axis.
Unless-
yeah, it's over.
Yes,
That's
of
it.
course.
It's an overestimate if the slope is going away from the x-axis.
Say that again.
It's an overestimate if the slope is going away from the x-axis.
Yeah.
Ah, interesting. So, in other words, if it's positive above and negative below, I like that.
And then it's the other way around.
Jesse, does that make sense to you?
Yeah.
Yeah, are you sure? Okay. Sarah? Okay. That's cool. I never thought about it like that. I'm very, step by step.
Yeah.
I don't make these grandiose things. That's good. I like that. Cool. Were you able to change this function though? Did anybody? I can't remember. Oh, yeah. You can put a different function in here. Did anybody do that? Put a different function in there? No.
I did it for the first one. Ooh, just now.
I'm like, you did not even do the
I didn't- I
assignment.
didn't.
Okay, all right. You just did it now.
But
Okay,
you can change it.
you can, yeah. So that's cool. I would encourage you that if you liked this one to play around with it again, you can change that function. Anything else from there? Self-explanatory, didn't teach with, I like this one, yeah. All right, easy to see the over and under. What was the over?
Oh, I think it's because I changed it.
Oh, you changed, you must have, because this is like 6 something.
Is the 6, the true answer? And the
Yes.
other ones are guesses?
Yeah, estimates. I don't like to call them guesses because they're actually pretty good estimates. This is right now, I think the one we're using, right? This is, I'm not sure exactly what the random means.
Try moving the more subdivision and see what the number
This one here?
Which one gets closer to 6.3?
is. Okay, so the real,
Yeah, this is the real one.
that's the real one.
The integral is the real one. These are all just the estimates that are changing.
You're at the right endpoint too.
Yep, so it could change depending on if it's
Midpoint.
midpoint. That one was kind of cool though too. I like that it had dotted lines so you could see that it was hitting in the middle. That was helpful to
So the
me.
midpoint might will be closest even with like
So, yeah.
less sub.
Yeah, look how close.
So even with just 31.
Yeah. Yep. It's close to 3, it's exact to 3 decimal places. That's pretty good. That's pretty good.
It's cool that this one related to the last one, like when it went under the x-axis, because they like swapped, like the other one did. When you went under the x-axis, it became like negative versus positive.
Yeah.
And this one they went like under to over. You know, like when the slope is negative before it goes under the x-axis, it's over, and then it's under.
Oh, an overestimate
yeah, like
and an
they swap,
underestimate.
yeah.
Yeah. Got it. Huh. I hadn't thought about it. Were you able to move this too? I didn't try that.
Yeah.
Yeah.
Oh, you are? Oh. Cool.
Now go to 100.
This one to 100?
Yeah.
Pretty cool. Pretty cool. Whoa, not so good. It's fun to mess around with, huh? How long did you mess around with these? Just curious. 10 minutes, 20 minutes? 34 minutes. Yeah, to be exact. 20 minutes or so? Just curious how much time you spent.
It's kind of easy to get the gist of where you're going with
Yeah,
like each section. Like it wasn't difficult to see what was happening
good.
that quick.
Oh, that makes me really happy.
Cool. it wasn't like, well, with the directions right there, you kind of knew what you're trying to get to.
Uh-huh, okay, good. All right, so some of you chose, this one's up here, the area function. Several of you chose this one here, which honestly, that surprised me a little bit, because I thought this one was pretty, was a little bit different than what we've been working on. So I was surprised that this one was the one that you, I guess I'm not surprised the one that you learned the most from, but maybe that you liked the most. Who knows, we'll see. I like this one because it shows you when you move the points to the left of the applet, the area was shown on the right applet. And so this is pretty cool. And you had to be sure to click the trace, right, on here. And as you move this nicely, you can sort of see what's happening here. Anybody know what that shape is? Somebody called it,
Parabola. That's what I said.
yeah, somebody called it exponential. I think it's probably parabolic. And if we can see it maybe a little bit even better. If we move this to 0, and move this all the way back. Huh. So, in some of your submissions, some of you said this one was the most confusing to me because I really didn't understand. I could see there was a connection between the two pictures, but I couldn't understand what that connection was.
Does that
It's
connect to
wrapping
the?
the area.
Okay, what?
Does that connect to the derivative? Because that's the slope of
Hold that thought for just a second. Hold that thought for just a second. Yes. What are you saying, Kendra? What is this one graphing?
The area.
The area under the curve, right? So as I moved this t a little further, excuse me, this x, a little bit further over and over and over, the area got bigger and bigger and bigger and bigger, right? And the area, we could probably say, was getting bigger by a quadratic, following a quadratic formula.
The
Some
X
sort of-
value represents the area, right?
The x value represents the area, absolutely.
On the right.
On the right, yes. Yes.
I don't know what the Y value
Wait.
No, the Y value is there.
No, the y value is the area.
Oh, yeah.
The
Y
x value is what's happening. I moved x. So what this is
X values are
saying
the same.
is the x's are the same, but this was on a t axis though. That's why that was a little bit trickier. The original one was a t axis, but my x was what was moving. Over here, x stayed still. So basically what this is saying is if you look closely here, like let's say here at 2, my area was 1. And you could probably figure that out here. Geometrically, this is what shape? How do we find that area?
Based on type of
Yeah, 1/2 based on height. So my base is 2, my height is 1, divided by 2, so I get 1. So that makes sense there, right? At 2, my area is 1. We could do the same thing over here at 3, 1/2 base times height, so 1/2, my base is 3, my height is, what do you say? 1.5 maybe? Tough to, looks like my slope is rise 1, run 2, so that's probably rise 1/2, run 1.
Look at the other one.
Yeah, well then we can look at the other one. What do you think it's going to be? Yeah, this I think is 3 half. Oh, maybe not. So you see, let's see, 3. So it's a little bit more than 2. Maybe 2 and 2 1/4, 2 1/3. Look at these numbers here. What do you think this one's going to be? What do we get here? 1/2 base times height. Does that look about right? What do we get here? 9 over 9 over 4. What's 9 over 4? 2 1/4. 2 1/4. Yeah. So that works pretty good. So this red line is representing what's happening to the area as these get further and further and further and further apart. Okay, now here's the sort of big connection, and Jesse and Kendra were onto it already. Do you think you can explain? Give it a shot.
Kendra, it's all you.
Well, the derivative of the integral is that, or, like, the derivative is the area under the graph. Like,
Okay, the derivative is the area under a curve.
or the graph of the area.
Okay, let's get our words right here. This is tricky. Another word for integral is
Area.
area under the curve. Okay.
So the area underneath the
So this area is quadratic. Would you agree with that?
Yeah.
Okay.
It's the one on the left, like F prime, and the one on the right's F.
Okay, let's see. He's saying the one on the left is f prime and the one on the left is f. Explain that.
So it's like X squared on the right and then X on the left for the slope.
Okay, so we know that this function, we're guessing that this function is an x squared function. And this function is a linear function with a
Yeah.
slope of, in this case, it looks like slope's maybe a half or something like
Yeah,
that.
it is.
Okay,
Yeah, that makes sense because it's also good. Like
So
the
it wouldn't be
degree
x
is
squared,
down.
but.
it would be something x squared. We'll call it a, we don't know what it would be, but something x squared. Okay? So Ryan said we're gonna call this one f and this one f prime. What is f prime again?
The slope.
Derivative?
Slope.
By looking at the area of the derivative, you can find the function.
By looking at the area of the derivative, so in other words, the integral of the derivative, you can find the function. Think about that for a second. By looking at say it again? The integral of the derivative. The integral of the derivative, you can find the function. What does that mean?
Go
Area
back.
below.
You can be given a derivative and find the function.
Okay.
Let's use your way of
We
finding
used to be able
function
to do
given
that
the
before.
Say it again?
We could have done that before.
We could have done that before. You're right. Let me connect this to some algebra that you've done in the past.
It's just gonna be able to calculate it.
Let's say I have, let me make it a different, let's say I have x cubed. What would I have to do to that to find plain old x? Cube root it. So way back in the day, you somehow learned somewhere along the lines that cubing and cube rooting cancel each other out, undid each other. Yes? Okay. So what Orion just told me is the integral of the derivative gives me plain old function. How is that idea related to this idea?
That is,
Are they the inverse of each other?
Don't I just end up with plain old x here? And if I take the integral of a derivative, I end up with the plain old function? Careful, they're very connected. They're not the same thing, they're actually opposites. They undo each other. Yeah.
no, I'm just saying with those two.
Oh, these two, yes, yes. I was talking about integrals and derivatives. Yeah, they're sort of the opposites of each other, right? They undo I don't want to say opposite, that's positive, negative, that's a mathy thing, but they undo each other. Do you remember way back when I gave you a graph like this, perhaps, and I said, graph the derivative function? You remember that? How did you do it? Do you remember how you graphed the derivative function?
Yeah.
You looked at the slope at each point, right? You found the slope here, and you found the slope here, and you found the slope here, and the slope here. and then you plotted those points. And we said there was a connection between that derivative and its, excuse me, that function and its derivative graph. And what was that connection between those two graphs?
It was a degree less.
It was a
Yeah.
degree less.
So it's
Do you
one
remember
area
that?
and it was- yeah.
Remember that?
Yeah, so if it was x squared, x cubed.
Okay, so let's see if we can put it all together here. If I have a function with that's squared, and I'm taking the derivative, its degree is 1
Less.
less. If I have a function and I'm taking the integral,
One more.
its degree is gonna be 1
More.
Do you remember how Stephen has all of these really cool little tricks? We're getting into some of those cool little tricks. Okay? Do you see how that might be one of those cool little tricks
So
that
we
he
could
has?
only draw a possible
Let's keep it warm.
graph.
Yes,
So now, if we can work the other way, we can work for this.
absolutely, absolutely. So why don't we take 2 minutes, stretch your legs, get a break, and we're gonna move into,
What was the next one?
it is,